Okay, so today we are going to go through chapter 10, section 10.2, which is vectors in space. So kind of like with section 10.1, where we notice a lot of similarities between things that we've already learned in the past in math. This is going to be similar to that as well. So we are going to kind of go back and review vectors. And that was a topic that some of you struggled with when we were doing it back in chapter 6. So this is a good chance to review and make sure we understand all the different aspects of vectors because we're going to be doing them again in 3 dimensions this time. So our objectives for this lesson is to find the component form of unit vectors in the same direction and dot products and the angle between vectors in space. Determine whether or not vectors are parallel, and then we're going to do one real life problem. Okay. So when we learned vectors the first time, we talked about how vectors are things that have both a magnitude and a direction. So things like force and velocity, they will both be vectors because they have a component of magnitude and direction. So we can also talk about vectors three-dimensionally because that's the world that we live in. So in space, vectors are denoted by ordered triples. So we had ordered pairs before, now this is ordered triples. So we have the 3 components that make up the vector. Just like in 2 dimensions, the 0 vector just means we're going to have 0 in all of those component locations. So the unit vector means that we have a 1 either in the x, y, or z location of the vector. So you can see I means that we are only going 1 unit in the x direction, j is 1 unit in the y direction, and k is 1 unit in the z direction. We also talked about standard form of vectors, so we have the I plus j plus k. So this would be unit vector form. So you can see here, these are our unit vectors I, j, k, and then this represents our vector that has the component v1, v2, v3. So if vector v is represented by the directed segment from P to Q, then the component form, if you remember when we did this last time, you're just subtracting the x values, the y values, and the z values to find your vector. So you're taking the x minus the x, the y minus the y, and the z minus the z, and that will give you the component form of the vector. These are a whole bunch of different things. We can kind of go through them briefly. So we know 2 vectors are equal if their corresponding components are equal. So if you go through those subtractions and all 3 components are equal, then the 2 vectors are equal. The magnitude, so remember we use those double lines around the vector. So the magnitude, remember, is the square root of each of the components squared added together. The unit vector is the vector, so the components, divided by the magnitude of the vector. To add the sum of u and v, we just add the different components. So if you're taking the sum or the difference of vectors, you're going to have a vector as your answer. The scalar multiple, same thing. We're taking a number times a vector. You're going to get a vector as the answer because it's just the number multiplied by all the components. The dot product, though, remember the dot product, we take each part of the component, multiply them, and then add the 3 parts together. This was a question on your test for chapter 6 that a lot of people missed. So be careful of the fact that, remember that a dot product is going to give you a real number out, not another vector. Okay, so example 1 is to find the component form and magnitude of the vector v having initial point 342 and terminal point 364. So, and then find the unit vector in the direction of v. So to find the vector, we're just subtracting. So 3 minus 3, 6 minus 4, 4 minus 2, that's going to give us the 3 components, which would be 0, 2, 2. So then the magnitude, we're going to take those three components, square them, and add them together, and then take the square root. So we get square root of 8, which we can simplify to 2 square root of 2. So then the unit vector, we take the vector, the component that we just found, and we divide it by the magnitude that we just found. So we're going to take, this is the magnitude, so instead of dividing, we're just taking 1 over the magnitude times the vector itself. So that would be 0 times anything, it's just going to be 0. 2 times 1 over 2 square root of 2, the 2's are going to cancel, so you're left with 1 over square root of 2, and same thing here. So then if we simplify, we rationalize that denominator. We're going to multiply top and bottom by square root of 2. So we end up with 0 square root of 2 over 2 square root of 2 over 2. So that would be the unit vector in the direction of v. Okay, example 2 is finding the dot product of two vectors. So again, remember our answer is not going to be another vector this time. It's going to be a real number. So the dot product of these two, we're going to take 0 times 4 plus 3 times negative 2 plus negative 2 times 3. So we get 0 minus 6, or negative 12. So, and again, it says, note that the dot product of two vectors is a real number, not a vector. So that's something important. Okay, so to find the angle between two non-zero vectors, you are going to, we did this as well before. Here's an illustration. We have vector u, vector v, so we're trying to find theta in between. We can use the dot product to find this. So the angle between two vectors, you're going to take the dot product of the two vectors and then divide it by the two magnitudes multiplied. And we talked about this before too, if the dot product is 0, then the angle between the vectors is 90 degrees, and then we call them orthogonal. Okay, so the example, so our unit vectors I, j, and k are orthogonal to each other. Okay, so example 3, we're going to find the angle between two vectors. So here we have vector u is 1, 0, 2, and vector v is 3, 1, 0. So we want to find that angle right in there. And we're going to do that by taking the cosine of theta. So we're going to take the dot product of u and v, and we're going to divide it by the two magnitudes multiplied. So we're taking these two. So where the 3 is coming from is we have 1 times 3 plus 0 times 1 plus 2 times 0. Well, we know those second two multiplications are just going to result in 0. So the only number you have is 3. Then where the square root of 50 is coming from is we're taking the magnitude. So 1 squared plus 0 squared plus 2 squared, that would be 5. And then we take the square root, so it'd be the square root of 5 over here. And then this one right here would be 3 squared plus 1 squared, which would be 10. So we have the square root of 10. So the square root of 5 times the square root of 10 is the square root of 50. So then to find theta, this is cosine. So we have the answer here. So we would do the inverse cosine of 3 divided by the square root of 50, and make sure that your calculator is in degree mode, and then you should get 64.9 degrees out. Okay, so the next thing we're going to talk about is parallel vectors. So we know from the definition of scalar multiplication that positive scalar multiples are going to have the same direction. So that's going to mean that they're going to be parallel. So if we can multiply a vector by a number and turn it into another vector, then we know that those two vectors are parallel. So this is an illustration of that. So here we have, this is v. We can multiply v by 2 and have it equal u. And then w is going to be equal to negative v. So these are still parallel even though they have opposite directions. So example 4 is to find vector w, or vector w has an initial point 1, negative 2, 0, and a terminal point 3, 2, 1. Which of the following vectors is parallel to w? So we have these two vectors and we're wondering which of them are parallel to vector w, which is between these 2 points. So the first thing we need to do is find the component form of vector w. So we would take 3 minus 1, 2 minus negative 2, 1 minus 0. So that's going to give us 2, 4, 1. So now if you're looking at this and then looking at the vectors that we're trying to determine whether or not they're parallel, you hopefully can kind of see if one of them can be multiplied by a number to turn into the other. So if we start with A, so we're trying to find out if vector W is parallel to vector U. And so vector U was 4, 8, 2, and vector W was 2, 4, 1. So if we look here, we can take this multiplied by 2 and turn it into 4, 8, 2. So therefore, U and W would be parallel. Okay, for B, we have vector V was 4, 8, 4, and we're trying to see, this is our vector W, 2, 4, 1. So we're trying to find a C value that we could multiply it by to turn it into this. So if we look at this, we can see, okay, we know 2 times 2 gives us 4, 4 times 2 gives us 8, but 1 times 4 gives us 4. So there's not a single scalar number that we can multiply this by to have it turn into this resulting vector. So because of that, they are not parallel. Okay, so you can use vectors to determine whether 3 points are collinear, so they're lying on the same line. So the points P, Q, and R are collinear if and only if the vectors PQ and PR are parallel. Okay, so our last thing that we're going to go through is an application problem. So this example is going to show us how we can apply this to real life. So here's our problem. It says a weight of 480 pounds is supported by 3 ropes. So here are your 3 ropes, and here's the weight that is supported. So the weight's located at the point S, which is 0, 2, negative 1, and the ropes are tied at the point P, which is 2, 0, 0. Q is at 0, 4, 0, and R is at negative 2, 0, 0. So we want to find the force, which we know is a vector, or tension on each rope. Okay, so what we're going to do first, we want to think about, so if we go back a slide, so this picture right here, so we can see that the force is going downward. So if we represent this vector right here as W, we know that it's going, the whole force is being applied down. So that is our weight of 480 pounds, okay? So W for weight is going to be 0, 0, negative 480. So we're going to find the force vectors corresponding to the ropes. So we're going to take the magnitude times the component of the vector divided by the magnitude of the vector. So for U, here's our component. So we're going from 2, so 2 minus 0, 0 minus 2, 0 minus negative 1. So this is going from S, which is the location of where all the ropes connect, to P, which is one of our points where the rope is tied. So that's our component. We're dividing it by 3, which is the magnitude of this vector. And then we're going to be multiplying that by the magnitude of U. So we're leaving this like this for a second. So we're going to do this for all of the 3 ropes. So vector U, that's how we're going to find, so the magnitude times this. Okay, so now V, we're going to do the same thing. So this is from S to Q this time. So we have our component, we have our magnitude, and we're going to leave that magnitude of V right there. Okay, now we're going to do the same thing for Z. There's your component, there's your magnitude, and we're going to leave it the magnitude of Z. Okay, so in order for the system to be in equilibrium, it has to be true that all of your different vectors have to equal 0, or the 3 vectors that we have just defined have to be equal to negative w, so the opposite of the force that's being applied. So, sorry, okay. So what we know is that we're going to have, I'm going to put them all out here so we can see. So we have a system of equations that we can write from this. So where these numbers came from, this right here, so these 3 numbers are the components of vector u that we found. So 2/3, negative 2/3, 1/3. And then this was what we found for v. So it was 0, 2 over square root of 5, 1 over square root of 5. And then z was negative 2/3, negative 2/3, 1/3. So if we go back a slide, you can see that those are, oops. Those are these right here. Those numbers are where we're getting the coefficients for the equation. Okay, and the reason it's equal to 480 is we know it's equal to the opposite of w. So w was 0, 0, negative 480, so it's going to be 0, 0, positive 480. So this is the system of equations, which we know how to solve a system of 3 equations with 3 variables. So in this PowerPoint, we're not going to go through all of that, but think of these as just u, v, and z, and you would solve for what does u equal, what does v equal, and what does z equal. So we could use substitution and go through and figure out each of those. So what you would find is that u equals 360, v is about 536.7, and z is equal to 360. So that means that the rope attached at point P has 360 pounds of tension, V has 536.7 pounds of tension, and Z has 360 pounds of tension. And that is so that the whole system stays in equilibrium in the way that it was drawn. Okay, so that is it for section 10.2. Again, always, please let me know if you have questions on anything from this slideshow or specific questions as you're going through the homework assignment. Thanks.